When a user types a command to read a file, like cat, followed by a file name, the terminal immediately returns the requested text. This instant response relies on the POSIX standard, an interface design where the operating system treats almost every stream of data as a simple, unified local file. But that uniformity is an illusion. Beneath the command line, the operating system is managing a highly fractured, heterogeneous namespace. The text we just called up could be written to a local solid-state drive, temporarily held in volatile RAM, or generated on the fly as a virtual representation of an active process. It could also live on a physical server located thousands of miles away. To understand how modern operating systems actually function, we need to look past the terminal and trace a single remote file read all the way down through the virtual file system abstraction and the network file system protocol stack. Before the software can organize anything, it has to deal with physical storage. Hardware block devices are sliced into partitions, and those partitions hold varying, often incompatible file systems. Looking at this storage organization, volumes 1 and 2 map cleanly to single partitions, but volume 3 spans multiple discrete physical devices. Managing this chaos requires strict logical architecture. Without it, the system would fragment, unable to reliably read its arrays. The mechanism that prevents this fragmentation begins the moment we execute our read command, kicking off a process called Pathname Translation. To trace this, we use a structural map of the operating system. The application sits at the top in user space, passing requests down into kernel space through the virtual file system and the NFS client, which finally connects to the network layer at the base. When the system receives the file path, it doesn't process the whole string at once. It parses the directory paths sequentially, component by component, moving down the tree. Eventually, this parsing hits a mount point. This is an empty directory used as a junction, where separate volumes or external network targets seamlessly attach to the main directory tree. The exact instant the path crosses the mount point, local directory rules cease to apply. The request is handed over to the remote network file system directory. Because the target is external, every subsequent component lookup requires a round-trip network transmission. These remote lookups introduce severe latency compared to local disk reads. To prevent the system from grinding to a halt during path traversal, the client machine maintains a directory name lookup cache, storing remote directory nodes locally to speed up future requests. Once the path is translated, the read request drops into the virtual file system layer. Here, the kernel faces a massive engineering problem. It cannot afford to maintain and execute custom directory routines for every possible file system type attached to the computer. VFS solves this by defining a clean interface. It decouples generic file operations like open, read, and write from their specific underlying hardware implementations. It achieves this using a structure called a Vnode, or virtual node. Unlike a standard local inode, a Vnode acts as a network-wide unique numerical designator for a file. Inside every Vnode is a function table. This table contains pointers that map those generic commands directly to the exact code required by the specific file system hosting the data. So when the user program issues a read system call, it executes blindly. The application has zero awareness of the underlying NFS protocol it just triggered. The virtual file system acts as the ultimate abstraction layer. It successfully translates a standard local request into an NFS-specific network action without alerting the user. With the action translated, the command drops into the network layer to be packaged for external transport. The NFS procedure serializes the file request into a remote procedure call, or RPC. Before leaving the machine, it uses a protocol called External Data Representation, or XDR. This resolves hardware architecture differences, such as varying byte orders or endianness, ensuring the request is readable by entirely dissimilar machines. The RPC then travels across miles of fiber to its destination. And this physical reality introduces a critical architectural constraint. The target NFS server is completely stateless. A stateless server maintains no open files table. It retains zero knowledge of the client's previous activities or current session state. Because of this, every single RPC request must be entirely self-contained, carrying the full file identifier and absolute data offset every single time it asks for data. This forces the operations to be idempotent. If a network request is dropped and repeated, it must yield the exact same result, guaranteeing robust crash recovery across a fragile distributed environment. But pushing an RPC fetch over a physical network for every single read operation creates an extreme performance bottleneck. To compensate, data fetched from the server is cached locally by the client, modified, and then eventually flushed back across the network to the server's master copy. This introduces a timing conflict. Local Unix semantics guarantee that writes to an open file are visible immediately to other users. But with NFS, Client B might read stale data because Client A's updates are delayed by network latency. Distributed file systems deliberately sacrifice strict immediate consistency. It is the necessary trade-off to maintain operational performance and keep network traffic from overwhelming the infrastructure. Once the remote server fulfills the request, the data makes its return trip. The packet ascends from the network, is unpacked by the NFS client, and routes up through the virtual file system, breaching the boundary back into application space. The terminal finally renders the requested text to the user. The requesting process remained entirely oblivious to the mount lookups, VFS abstraction, and RPC serializations that just occurred in the background. This illustrates the core design philosophy of a modern operating system: the ability to treat a server located half a world away exactly like a local sector on a spinning disk. This seamless behavior is only possible because the operating system strictly enforces clean, rigid interfaces between its software layers. Abstraction layers like VFS do not eliminate system complexity. They merely contain it, keeping the chaos of physical hardware and distributed networks hidden beneath a simple, unified command.